So, good evening. Today's lesson is going to be on 1D vectors, so one-dimensional vectors. This is for the Canandaigua Academy's first year IBAP physics class. So, before we begin to talk about what a vector is and isn't, consider the following situation. Let's say that I am hiding from you, and all I tell you is that I start from my desk and walk 4 meters, then 8, and then finally 10. So there's two questions that naturally follow this. Is that how far did I walk? Well, if I want to just know how far I walk, I simply take the 4 and the 8 and the 10 and add the 2. So I get 22 meters. So another way of asking this is, what is the distance traveled? So in a situation where someone's hiding, what's really more important is where they are hiding. And if you ask yourself, where am I hiding based on the given information, you don't know. And you don't know because there's a very, very important piece of information that is missing, and that is the direction. So to ask yourself, where am I hiding, really what you want to know is where. I started at my desk. What you really want to know is what my final position is, or in other words, my change in position. And that's also known as the displacement. So what is the displacement? And so displacement is a change in position. So what question is more informative about his position? Which question is more informative about his position? Is the displacement. The displacement will tell me where I am at the end of it. So the important lesson to take away from this is that direction is actually more important than the magnitude, or equally important when we're dealing with measures of motion. So we categorize all types of measurements in one of two categories. We have scalars, and those are quantities with just magnitude only. That is your how big, how fast, and how far. And this could go on and on and on. And there are another category of measurements which we call vectors. So popularized by the movie Despicable Me. Let's take a look.
Hey. I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah!
So vector is the character committing crime of both direction and magnitude. So the magnitude part, as once again, is your scalar information, how big, how far, how fast, and then the direction is in which way is that person moving, or how big. And he also mentioned that it's a quantity that we're going to represent with an arrow, okay, and the arrowhead points in whatever direction we're trying to travel. And typically we're going to pick a direction to be positive or negative. So if I pick up to be positive, then it means the consequence of that is anything moving down is negative. And if I pick something to move to the right to be positive, the consequence of that is anything moving to the left is negative. And we could say this for northeast, southwest, etc. So examples of quantities that we'll talk about this year that are scalars is time. Time just has an amount. It does not have a direction. Mass, distance, speed, energy, And we can add on to this list, but these are the first couple that we'll see earlier in the year. Vectors are our displacement. We said before it's a change in position, so there's a directional piece of information there. Velocity, acceleration, momentum, and force. And once again, this is not a complete list, but this will kind of get things started. So all of these pieces of information on the right have both the magnitude and the direction. So both pieces are just as important as one another. So how do we deal with addition and subtraction? This is going to be different than what you might have done in your algebra class, because algebra class, you're not dealing with things going right, left, etc. So when we're dealing with addition, an algebraic method for dealing with 1D vectors is if they're going in the same direction. If two or more vectors are going in the same direction, then all we have to do is just add the magnitudes. If they're going in the opposite directions, if vectors in opposite directions are given opposite signs. So if I know something is moving to the right to be positive, then I'll make everything moving to the left to be negative, etc. And then I add them. So let's say an ant crawls 2 meters up and then 4 meters down. If I want to say that up is the positive direction, then down must be the negative. So I can take my 2 meters and I'll call that to be positive. And I will take my 4 meters, but since it's moving down, I will put a negative sign in front of it. And then positive 2 plus negative 4, we get a negative 2 meters. And another way of expressing this is since the negative tells me it is moving in the downward direction, I can also write this as 2 meters down. So this is my magnitude and that is my direction. Hence, we're talking about the vector of displacement. For subtraction, the easiest method for subtraction is to make it an addition problem. And what I mean by that is another way of writing a minus b is a plus negative b. And then now we can just use the same rules as above. So if I have a displacement of 20 meters north and I want to subtract 10 meters south, then what I can do is I can make this as 20 meters north plus a minus 10 meters south. So another way of writing minus 10 meters south is actually a positive 10 meters north. And then if I'm now adding these, they're going the same direction, they have the same sign, this is equal to 30 meters north. Or you could just say positive 30 since we've arbitrarily chosen north to be positive. So I just want to point out something at this juncture that not all vectors are going to act in the same line. Okay, and this is what we're going to be dealing with next, two-dimensional vectors. So when two or more vectors act not in the same line, we can't use the positive and negative sign. Instead, we have to use a little geometry and trigonometry. So an example that what I'm talking about is if I have velocity vectors of 6 meters per second south and 8 meters per second east, I simply can't add or subtract them. I have to create a triangle. So if I base it off of the coordinate system that up is north, down is south, east, west, then I have 6 meters per second south, and I have 8 meters per second east, then really what I want is the third side, aka the hypotenuse of that triangle, and since south and east are perpendicular to each other, then I could just use my Pythagorean theorem. So we're not there just yet, but I just want to point out this: the addition rules for addition and subtraction that I just mentioned only apply for when they act along the same line. So this can also be applied when we're talking about relative motion. And so another thing that's very important about relative motion is choosing a frame of reference. So to illustrate this, I took a video of when I was in the airport walking along an escalator. So you can see I'm walking because you see my feet moving. Okay. However, if you notice that relative to this pole right here, I am not moving relative to it. So although I'm moving relative to the escalator, I am not moving relative to the person taking the video. And you can see this person that just walked by, that they were moving relative to the person taking the video. And we can say that they might be moving, just based on the speed, this is an assumption, that they were moving with the escalator and I was moving against it. So in other words, my velocity and the escalator's velocity canceled out to someone relative to the stationary ground. So let's consider a cruise liner cruising at 30 kilometers eastward. And we have a bicyclist moving at 20 kilometers towards the back of the boat, or aka west. And they toss a moldy bagel at a speed of 5 kilometers per hour. So if we assume that everything moving to the right is positive, then both the bagel and the boat are moving in the positive direction and the bicyclist is moving in the negative direction. So if I want to know how fast and in what direction the boat, bicycle, and bagel are moving, those are 3 separate questions, but I first have to ask, what is my frame of reference? So we're going to say that it's relative to the sea. So the velocity of the boat is straightforward, that if it's moving in the positive direction, I'm sitting here watching all this go by. And I would just say it's moving at a positive 30 kilometers per hour. Or I could say 30 kilometers per hour east. Now the velocity of the bicyclist is it's moving, but the boat is also moving. So I actually have to take into account both velocities. And so I would say the boat is moving 30 kilometers. Remember, we're basing this off of the sea. The boat is moving at a 30 kilometers to the right, and then the bicyclist is moving at a negative 20 kilometers an hour to the back. So if we add the negative, that's the same as subtracting it, and I get a positive 10 kilometers per hour east. So although they are moving to the back of the boat, they're not moving to the back of the boat fast enough. So if I'm standing stationary in a small boat watching this all go on, I actually see the bicyclist moving to my right, even though they are pedaling relative to the boat to the west, to the back of the boat. And then the velocity of the bagel, I have to take into account the velocity of the cruise liner, the velocity of the bicyclist, as well as the velocity of the bagel itself. And I would take the 30 kilometers per hour. I would add the negative 20 kilometers per hour for the bicyclist because it was moving before it was thrown. And then I would add the 5 kilometers per hour of the bagel itself. And if you take all these and add them up, you get a positive 15 kilometers per hour to the east. Okay, so in all these situations, what did I do? I added the velocity vectors of all objects except the ones in the frame of reference in question, which in this case, the frame of reference in question was the sea. Now we have a slightly different problem. Let me just get this all onto the screen here. we have a similar problem, but now we have on a highway, a Volvo is moving 10 meters per second west. So there's the Volvo, 10 meters per second west. The Audi is moving 40 meters per second east. And the Chevy is moving at 30 meters per second west. So if I want to know how fast the Audi is moving relative to the Volvo, what I have to do is I'm going to take the velocity of the Audi to be positive 40 meters per second. But think of it this way. They are getting closer to one another. So they're moving at one another. So if I say that there's a negative 10 meters per second of the Volvo, then really what I need to do is I need to subtract the negative 10 meters per second. And what this ends up being is subtracting the negative is the same as adding the positive. So this is positive 40 plus 10. And so I get a positive 50 meters per second to the east. Okay? And if I want to know the Volvo relative to the Audi, well, I just flip that around. I have the negative 10 meters per second, and I'm going to subtract the 40 meters per second, or subtract the positive 40 meters per second. So no matter which way I look at it, I get a negative 50 meters per second. And actually, I'm going to take away this eastern part, because all this tells me is how they're moving, how fast they're moving, and it doesn't tell me the direction, because we're talking about things moving at one another. So I'd say negative 50 meters per second. And then the Audi relative to the Chevy, well, I'm going to take the same approach. Then I'm going to say it's positive 40 meters per second, and I'm going to subtract the negative 30 meters per second. So what I end up getting is adding the negative, I end up getting a positive 70 meters per second. Okay, so the lesson of this is from a common frame of reference, which in this case, the frame of reference was all the ground. We all were given speed relative to the ground. The relative velocities are determined by the subtraction. In other words, that if I want to get the velocity of A relative to B, I'm going to take the velocity of A relative to the ground, that's our common reference frame, and then subtract the velocity of B relative to the ground. And so this is an equation when you have a single frame of reference. Excuse me, a common frame of reference. Okay, all of the speeds are measured relative to the same reference frame. Okay, so that's all for now. Thanks for listening. Bye-bye.